Welcome back to che531. In this video, I'll be talking about built-in functions in Matlab that we can use to find the root of a function. So the first function we're going to look at is f0. So this is a function in Matlab, and the way we actually use it is we introduce the function, we give initial guess, and Matlab is going to find the closest, perhaps, root, to the initial function. The convergence I think that Matlab is going to use is what is called relative convergence. So it means if xn is the current iteration or the solution from the current iteration, xn minus 1 is the solution to the previous iteration. It finds the difference between the two, divide by the previous iteration, and if this is less than, let's say, some threshold that is given by the user, then Matlab is going to stop. Basically, it's going to find, or declare. It's going to declare the root as xn. Okay. So a couple of things that we have to note. One is we have to make sure that the function crosses the x-axis before we try to solve the root. Because if the function does not hit the x-axis, that means there's no root. And even if you solve it by Matlab, 100% we should not get anything. Because there's no root, for the function. Another thing is, if our function is the absolute value of another function like that, then Matlab is going to throw an error, because when we have absolute value, then we have derivative divergence at the point that the curve hits the x-axis. Because of the absolute value, we're going to have two derivatives, and that means the derivative is not defined, and as such, when you use Matlab f0 function, you run into error. Okay, so let's go back to the script and see how we can use f0. So here is a script that I've written. Example 1 is z tan z minus some constant c, which is now 1. As always, we're going to plot the function. I think we've seen this function before. Because at z equal pi over 2, the function is not defined, I'm just going to move my lower bound to a little bit away from pi over 2. Okay, so that's why I have pi over 2 plus 0.1 and minus 0.1. So I'm going to have 50 points. I have my z, then I can calculate my f of z, and down here I'm going to plot it. So let me just put a breakpoint here and look at the function. So the function is going to look like this, and here's the x-axis right here, and it hits the x-axis twice, one around here and one around there. Okay, so let's see which one we're going to find. So here is the function f0 that I'm using. I'm introducing my function within the function. So this is f0 function. Within that, I define my function, just x tan x minus 1. And I'm telling Matlab that this is only function of x. So at x space and then the function, comma, initial guess, let's say 1. And options, within options, I define my tolerance by this tol x. That's the keyword. I'm setting my tolerance to 10 minus 5. And I'm going to show the iteration progression. So as Matlab, cycles through different iteration, we're going to see, the error, the solution, whether it converge or not, and things like that. Okay, so I passed these into options through optim set, which is Matlab command, and then I pass this options into here and solve for the root of that. So on the output, I'm going to see x, the function at x, the exit flag, which means whether it converged after exiting or diverged after exiting, and then some other outputs that I can't remember when. Well, we're gonna see it after I run it. All right, and after we got the solution, we're gonna plot. So I'm gonna plot x, and in fact, I'm gonna plot f of x as a function of x. Okay, then my f is also a function of c, the constant. And I define my function down here, which is x tan x minus c, but in this case c is 1 because I said so in the first line right here. Okay, so then we can also plot a function. For the root, I'm going to put a red points. or just rent one breakpoint because there's only one solution. Okay, so I think now we can go ahead and continue. And there you go. So I use my initial guess of 1, and the solution is somewhere close to that. And you see that it's shown by red point. Then let's look at output. The solution is 0.86, which is close to 1. All right. These are iteration. Actually, let me go back. So it shows how many iterations have passed so far. F0 actually uses bisection method. So you see two outputs, A, the left bound, B, the right bound function at point A, and function at point B, f of B and f of A. And then some information which is not really important in this class. Okay, so this is the basic total number of iterations. And then the solution. So I think this is the lower bound, upper bound, as well as the average. So we know that in bisection, x is going to be either the left or right, depending on which one changes the sign in every iteration. So I think if you go back to the theory of bisection, you remember how we can calculate, how we can basically replace x or a by x or b by x. Anyway, so this is the x, and you see that it goes down. Actually, it goes up, but at some point you see that x doesn't change anymore, which means that's the solution. Okay, and we also get f of x, which is going to 0. I mean, that's supposed to be the root. And procedure, I think that says something about what method within the bisection has been used, to get this root. And so 0 found in the intervals, some just interval, that for you to know that the root is between these. So here's basically the real root, and here's the function evaluated at the root, and exit flag 1 means converge and exiting. Other flags you can Google in Matlab. Let's say F0 exit flag. You see a list of them in Google or in MathWorks help. So you can basically go ahead and see what each flag means. Okay, some other outputs. See, it says it's using bisection with some interpolation. So it's a combination of bisection and interpolation. It has gone through six interval iteration, four iteration, and 16 function evaluations. Now these are not so much important, but just pointing out that what each means. And at the end, it says 0 found, so that's what exit flag 1 means. So the 0 was found within this interval, and that is it. So that was F0. Okay. So next function we're going to look at is Symbolic Solver, which means now imagine we don't want to solve anything numerically. I have a function of, let's say, x, or maybe a and b and c, some other constants. And I want to solve for the root exactly, or we call it analytically. Okay, so there's no numerics here. For that, we're going to use solve function. So solve in Matlab requires the function itself and the independent variable. That means we're going to solve f in terms of x. Okay, so x is going to be the solution of the function. So for this, because that's symbolic, we do not need any starting point. So the starting point is actually not needed here. Let's go back to Matlab and see how that works. So I'm going to comment out these examples because we talked about them. And in fact, highlight all of them. Comment out these and these. And the function definition, we don't need that. All right, so here's a symbolic. So let's look at this example now. I'm saying C is a symbol, okay? Now I'm saying, all right, so please go ahead and solve func x, which I had here. I think I should, yeah, so here's my func. I need actually to uncomment them. Okay, there we go. So here's my func, which is x down x minus c. So what I'm saying here is c is constant, or it's a symbol. Please go ahead and solve f or func of x and c in terms of x only, assuming c is constant. And oh, actually, sorry. So actually, func is right here, so I need to comment this. All right, so my function is x to the third power minus some constant c. I'm saying that c is constant, x is unknown, so I'll solve for x. Let's go ahead and solve it. In fact, I forgot this, and I need to comment that out. All right, so it's thinking, and there you go. There are 3 roots. We know that it's a polynomial. It has to be 3 roots. One is this, the second one, and the third one. And if you notice, c is a constant, so we don't need to know what the numerical value for c is unless we really want to evaluate every root numerically. But for now, everything is symbolic, so you see that it's actually everything is based on c. And if you see I here, I means, if you remember, it's imaginary number, it's square root of -1. So now you see the solution gets a bit crazy because now it has I in it, so that means the solution is imaginary. It has imaginary part and real part, okay? But the middle one actually is only real. So the first and last are imaginary, the middle one is real. It's pure real number. Okay, so that's how symbolic works. You can basically try solve any functions you want in terms of any other variable, but you have to say which one is variable, which ones are constant. Okay, so I'm going to comment these out and look at the third function in Matlab to solve for the root, and that is basically used to find the root of a polynomial. The function is called roots, and within roots we give the coefficient of a polynomial and then we get back the roots. Okay. Okay, so roots is the function in Matlab, and you only get 1 roots actually. Actually, no. I think it returns all roots, but let's try. So here is the script for polynomial root finder. So we say, okay, so we have to introduce the coefficients, basically coefficients of the polynomial, and then ask roots to basically find the root. The question is, what are these coefficients? And I believe I should have talked about them before. Let's search for coef. Actually right here, example 2, yes. Okay. So what I'm trying to solve here is a polynomial of order, let's see, 1, 2, 3, 4, 5, order 4, okay? And these are the coefficients of 4th order polynomial, 4th order terms, 3rd order term, 2nd order term, 1st order term, and the constant term. So these are called coefficients for the polynomial. And I'm trying to find the root of that. So before doing anything, I just like to plot. All right, so where is the line? Okay, let me see. So here we split our z-axis from -2 to 2 with 100 intervals. We evaluate this polynomial, so it's poly-val. That means evaluate the polynomial with the coefficients that I have here and the z-value that I introduce here. So with this z and the coefficients, we're going to get f of z. And we should go ahead and plot them like so. So here's the function, and there are 2 roots right here, and I'm trying to find them. Okay, they're 2 real roots, by the way. Okay, so the function again is called roots. We give the coefficients, we get the roots back, and here are the roots actually. So there are 2 imaginary ones and 2 real ones, total 4 roots. That's true because it's a 4th order polynomial. It has to be 4 roots. And at the end, we're going to plot. We're going to evaluate the function at the roots. Right, I have x1 as the root, all 4 roots, and I'm going to plot them against x. And so that's where we see only 2 of them because 2 of them are real. The other one is imaginary. Imaginary ones are not plotted. Okay, so that was only the roots only is used when there's a polynomial. Okay, we cannot use roots for any other function. It's a polynomial root finder. We talked about fsolve and we talked about f0. So the 3 functions that you know we can use to find the root of a function. Okay, so that was it. Thank you so much for watching, and stay tuned for the next video on solving the root of a multidimensional function.